Okay, so let's have a quick review. This next one, you inherit a watch, your increases at a rate of 4.2% per year. Find someone that was here on Wednesday and go over it with them. So we're going to jump to these last two. Okay, these last two, the population of Utah, and this is what we did not get to in class. So this will be good for everybody. The population of Utah was 2.233 million in 2000. And then 2.763 million in 2010. Now this is so it's gonna follow an exponential model, but this one, so population change is more of a continuous idea. So there's people constantly, especially in big cities, constantly being born, dying every day. I mean, you could have hundreds of births, hundreds of deaths a day. So it's hard to pinpoint that on an exact moment where it grows. So it's more of a continuous growth. So we're going to use the continuous model. So your continuous model, the outcome is going to be the initial value times e to the k times t. Now we need to find the k. So the k is kind of your rate of growth, and that's what we don't know. We're given two sets of data. So we got the year and the population. So in the year 2000 we were 2.233 million, and then in the year 2010 it jumped up to 2.763 million. Okay, so let's find k. Now k is going to be an unknown in the exponent, so the only way we can solve for k is to use a log. So we are going to take this set and we're going to use this right here. So we're going to say the initial value is going to start off in 2000. So my initial value, a, is going to be 2.233. So that's what we started off with. And we ended up, I know what we ended up with. I ended up, so that's my y, I ended up with 2.763. Okay, I'm going to times that by e, which is kind of my continuous change, my 2.71. Raise it to the k. I don't know the rate. I don't know how fast things are changing. But I do know that I went from 2.233 to 2.76 in a time period of 10 years. Okay, so if I plug in everything that I know, I can work backwards and solve for k. So first thing we got to do, we're going to solve for k. I got to ditch the 10, I got to ditch the e, and I got to ditch the 2.233. So let's inverse the times. Let's undo the times. If you divide this by 2.233, I'm going to divide this side by 2.233. Okay, so let me do that real quick on my calculator, so these decimals might get kind of messy. 2.763 divided by 2.233. And here's my next move. I got 1.2375, and you don't want to round. Take as many decimals as you can. The more decimals you use, the more accurate your answer is going to be. So now I've got e to the 10k. Now I've got to undo the e. And the only way you can undo a base, inverse a base, is to morph it to a log. So the log has 3 components, and I just got to drop each piece in the right place. So the e is the base, so log in base e. And if you ever have a log in base e, that's the natural log. So log in base e, the e goes there, the 1.2375, that goes here. So I'm going to draw an arrow, that goes in there, and then my 10k goes here. And this is calculator. You've got to just punch that in your calculator and it will return you some value. So if I go log in base E of 1.2375, or you can do ln of 1.2375, that's going to equal 10k. So let me do that real quick. So I got this 0.212971 equals 10k. Now you just got to inverse the multiplication. So divide by 10, divide that by 10, and we end up with k is equal to 0.021297. Okay, now, so that's my rate of growth, 0.021297, or if I'm looking at percentages, that's like a 2.1297% a year. So in that town, the population is increasing, in Utah, the whole state, so a little more than 2% a year. Now you know the rate of change, 2.1297% a year. So let's use that. We got to use that to answer B and C. So B, once you found that rate of change over the past 10 years, we're going to use it to kind of predict future models. So we're going to predict, let's say, assuming the population continues to grow at that same rate, let's predict the outcome in 2030. So 2030, from 2000 is going to be a difference of 30 years. So my model, getting kind of cluttered here. So my output is going to be my initial value, which was 2.233 times E. Now for K, you got to use the decimal. Don't use a percent. Change it back to a decimal. So we're going to go 0.021297. And for T, for time, we're going to put 30 years. So this one, everything's on one side, so you just punch it in on your calculator and hit enter, and it should spit out what you want. So there's no undoing, no inversing, so it's straightforward. 2.233 times E 0.021297 times 30, and we're going to get Y is equal to 4.23023, and that's million people. So we're going to predict 4.23 million people in the year 2030. Okay, now C is not as easy as B. So let me get a clean slate here. Okay, here's what I know. My rate of change was 0.021297. Okay, C. When is the state going to reach 3.5 million? That's actually my Y. So if your model is Y equals A times E to the KT, that is going to be the outcome. So if I put 3.5 in there, so it's going to be 3.5 equals my initial A was 2.233 times E. My K, I know, I found that, my first thing, so that's 0.021297 times, this time, I don't know how many years it's going to take to get to 3.5, so that's my unknown, that's my X. And it is in an exponent, so we're going to have to undo all this, and that's going to require a log at some point. So first of all, let's get this E by itself. Let's undo this times. So let's divide 2.233 on this side, divide this side by 2.233. So 3.5 divided by 2.233. Okay, we got 1.5674 is equal to E to the 0.021297x. Okay, now I'm going to undo the E, so I'm going to log. So I'm going to go log base E of 1.5674 equals 0.021297x. Okay, now my calculator, I'm going to punch this in and change that to a number. So if we do log base E of 1.5674, we got 0.449418 equals 0.021297x. Now I'm going to divide by that, divide this by 0.021297, and that should give me the number of years it's going to take. 0.021297. Okay, so X is going to be 21.1024 years. So it's going to take 21 years for that to happen. So if I start in 2000, by the year 2021, I should reach close to population of 3.5 million. Okay, now D, find the doubling time. So my K was 2.1297%. So find the doubling time. So how long is it going to take for my population to double? So let's use that rule of 70. So if I take 70 and divide it by 2.1297, so it's almost cut in half, about 35 years. 70 divided by 2.1297, it's going to be 32.8 years for that population to double.